Okay, great. So thanks for the invitation to come address the group here. It was some excellent discussion there. The questions that you guys are asking are, I think, right on point with some of the issues and challenges that we're seeing with AI today. So the interesting part for me, going like fourth in line here for presentations, is most of the groundwork's been covered already. So that's the good news. I've got a couple of slides that we're kind of going to gloss over. I don't think we need to see any more history of AI and deep learning. So we'll go ahead and get started. But AI is everywhere. So we're going to start off here. It's a term that's being used rather ubiquitously now, similar to cloud computing, big data, those types of big terms that describe lots of different things. So in some of the previous presentations, we've kind of started to peel that apart and understand what compromises AI, the different components. So as we move forward, a lot of our focus has been around the deep learning component of AI. So, the punchline is that it is a high-performance computing problem. I don't know that anybody would necessarily disagree with that. We're able to deliver benefits similar to HPC and other disciplines. The value is really in the decisions that are enabled. There's a large amount of computation, large amount of data motion, I/O, and network. This all sounds very familiar to this group. HPC technology and best practices apply directly to deep learning. So behind the scenes, really what we see is when we start looking at deep learning training is computationally intensive training phase. We process samples, we compute gradients locally, we globally average of the gradients, wash, rinse, repeat. We keep doing this over and over again. So you guys can see where HPC, fast networks, lots of computational power really help to enable speeding up the training cycles. So why are we here? So faster is better. I think we'd all agree with that. But it's also communication intensive. More accurate is also better, but that's computationally intensive. When we look at what we do within HPC around high-performance simulation, a lot of those same core tenets apply for high-performance machine learning and deep learning. All right, so we're going to use weather as an example. Cray, we like weather and people that predict weather. So this is an example that NERSC did. This is more based off of traditional HPC simulation and modeling, but we know that more accurate is better. At 100-kilometer resolution on top versus 25-kilometer resolution on the bottom, there are certain things that you miss. So tropical storms and cyclones developing, big waves up to 30 meters, fairly significant size there, are missed. So we know faster is better, but this higher resolution simulation requires 64 times more computational power. So that's where, as we start to train on larger sets of training data, then more computational horsepower is needed to reduce those training cycles down. Does anybody watch the show Silicon Valley on HBO? All right, we got a couple of people. Very good. All right, so latest season they had a great episode where one of the software developers was developing an AI application to identify types of food. So they quickly tested it out, took a picture of a hot dog, and it came back and it labeled it correctly as a hot dog, right? They were all celebrating. This is the next unicorn app. We're going to go build a company worth $1 billion and then sell it off to somebody. They then proceeded to take a picture of another type of food, and it came back and it said, not a hot dog, right? So this is a good example where more data is better. Just training on very specific types of use cases and outcomes and results starts to lend bias. So. Okay, HPC and AI will converge. We've heard a lot of the big kind of luminaries in the industry talk about this. Andrew Ng talks about using HPC technologies for deep learning and leveraging them for deep learning. We know that digital data is doubling in size every 2 years. Estimates by 2020 is going to reach 44 zettabytes. There was a study that was done by the folks at Inside Big Data They did some surveying and some polling and found that 28% of the respondents believe that HPC will allow them to scale computationally and build deep learning algorithms that can take advantage of high volumes of data. So we're starting to see that the user community and the constituency is seeing the value here. Another great example is we can expect to see a 40% reduction in error when 10 times more data is used. And this is a specific example around AI and speech recognition. So again, I'm really trying to drive that point home. More data is better. It helps with the quality of our learning. Okay, this has been covered, I think, ad nauseum here in the previous presentations. I don't know that we have a different view. I think that's the good news. Really, AI is kind of the umbrella term where all these other technologies fit underneath. We still view analytics as being a fairly important part of the process. There's a certain maturity model that comes along with aspiring to do artificial intelligence, and it absolutely starts with analytics. Analytics is where you start to get familiar with your data, where you start to understand what type of data you have, you start to understand the quality of the data, and really the confidence factor that you have in that data. And then as you start to move down that continuum, you start to be able to leverage technologies like machine learning, both unsupervised and supervised, and then that's where we get into deep learning, which it tends to focus on use cases around vision, speech, language, those types of things. Okay, so we've got a couple of sightings here from Gartner's top 10 strategic technology trends and Fortune magazine. But the real kind of key takeaway here is, according to Gartner, extensive parallel processing, advanced algorithms, and massive data sets to feed the algorithms has unleashed a new era. I think we would all agree with that. That's why we're here today, talking about this. Going back a little bit further, though, Fortune fast data is just as important as big data. We've heard a lot of talks around, a lot of emphasis on streaming data and the ability to kind of quickly bring in new data to train on, making those training cycles shorter so that we can update the neural networks to new types of scenarios. In a competitive economy, this supercomputing becomes essential for these types of things. So it's a solution for strategically important problems, maintaining global leadership in industry, government, and academia, and creating next-generation technologies, products, and services. That's how a lot of the commercial world is looking at AI and the benefits that it can provide. Okay, another great paper by Forrester. An AI revolution started for courageous enterprises. I think we would all agree that the organizations that have AI proof of concepts underway or are leveraging AI in some way are at the very bleeding edge right now. We know for all the promise of this technology, we can find 100 examples of how it's failed or how it's done something wrong, and that's typically is retraceable back to bad training data, data that's labeled incorrectly, neural networks that didn't account for certain types of scenarios. So, what does all this mean? Deep learning is worth it. But the other key thing, I think, from an HPC perspective that the Forrester paper calls out is that you should expect to need thousands of cores. This is absolutely an HPC problem. Okay, so our friends at NERSC, they've been playing around with deep learning in support of some of their classic HPC simulation and modeling. Things like galaxy shapes, decoding speech, extreme weather events, LHC events, so on and so forth. So we're starting to see not necessarily a replacement of HPC simulation and modeling, but we're starting to see these types of technologies deployed in conjunction with those methods and techniques. So we did a deep learning workshop at HLRS earlier in the year, and Daimler presented kind of their view on how they thought deep learning could add value to their business and specifically to their design process. And really, what they saw was that it has the potential to do an automatic evaluation of results in complex, multi-component, non-linear applications. So this is where we start to evaluate, instead of just a single component, we start to evaluate systems of systems and clusters of components that comprise a system. And then we start to understand the impacts and how those components interact with each other, and then how they can ultimately impact things like the noise and vibration and harshness that the driver is going to experience within the automobile. So here's a couple of examples in manufacturing. So I'm going to skip over autonomous vehicles. We had a wonderful presentation from the folks at Nissan yesterday that really, I think kind of highlights what's going on there. Aerospace drones. We routinely have a lot of discussions with organizations that want to process data from drones, both in an aerospace, a defense construct, as well as we've also had conversations with airlines. They want to leverage drones to do aircraft inspection. Let's train the model to detect faults in an aircraft that might go overlooked in a physical inspection, visual inspection scenario. The drone can perform the task a lot quicker. It's not necessarily feeling rushed that it needs to perform a visual inspection in less time than it should take. Can probably more accurately identify problems. Another technology that we're looking a lot at, concept is digital twin. So this ability to kind of, understand that, create a model of, a particular complex system, and then be able to predict failures under certain types of environmental conditions. This is incredibly helpful for, obviously automotive and aerospace, but other types of technologies that are exposed to a wide variety of environmental conditions. Okay, so we did some work with a group called the Innovita Partners. So this, again, very survey-driven type of exercise. But what they found, so this was focused on folks that work in the financial services sector, and really, we'll start at the small circle graphic in the top left there. 85% of organizations are in some stage of a POC, either around deep learning or machine learning. 15% of those have actually have things in production. I think that's the really compelling part. But along the bottom here, what we're kind of describing is the timeline to ROI, and you can see with a year in. A very small number of organizations are kind of reporting success with that, or an impact to ROI. When we get to that 1 to 2 year mark, it starts to increase. But I think the key takeaway from the responses to this survey is that this is it's a long-term investment, and it's not a piece of technology that you go acquire from a vendor and you plug it in and you start pushing data through it and it starts giving you wonderful answers. There's a much bigger investment. We've heard a lot of discussion earlier today about the ecosystem that kind of surrounds AI and deep learning, and it's there's certainly an engineering, there's a data science component to that. I thought it was interesting that in the presentation from Nissan yesterday, they mentioned that they had anthropologists as part of their team working on their autonomous vehicles, and those are great examples where this is just such a bigger problem, right? And how we solve for it, and the skills and the expertise to do that are much different, I think, than some of the problems that we've solved for in the past. Okay, so I think we've seen this one in various stages and forms, so I'm not going to spend too much time on it. But we've kind of had the history lesson a couple times here, so we'll go ahead and skip past that one. So some of the challenges. So in the Forrester Tech Radar report, AI systems are still demand considered design, knowledge engineering, and model building. So it's not a COTS piece of technology that you install, configure, and leave it be. So they involve large complex workflows, different toolkits, data movements, and networks. This piece is fairly important, and I think it's been highlighted quite a few times in some of the earlier talks, in that the ecosystem the open source toolkits that are available, that space is evolving very rapidly. And we saw this a lot within the big data analytics space, when we kind of started with Hadoop, and now we see Spark and a bunch of the other memory resonant types of database applications. This space is changing very quickly as well too. So we want to make sure we're keeping an eye on what technologies are excelling, where the adoption rates are, and then more importantly, when we talk about data movement network, these are paramount HPC problems that we've been solving for a long time. And really the key is, when we start to look at workflows, it's not a serial workflow where we hand off data from one system to another. We know that's the delays just in the handoff process alone are too large. So training times grow with data size and complexity. We know we start off with something that takes days. It's going to evolve to weeks. When we start to tune hyperparameter optimization, that goes completely crazy. So. So really, we're seeing a lot of deep learning platforms that are, dense GPUs. I know Intel's got a big push into this space as well too. I think the real key takeaway here, though, is that when we talk about the ecosystem, there's a number of ETL functions that still need to occur. There's a bunch of analytics functions and machine learning functions that still need to occur. So it's not one dense GPU system that you buy that handles all of these things for you. So it's in context, it's an architecture, but it's kind of ideally tuned for the problem space that you're solving for, the size of the data sets, and training data. And of course, we keep going back to HPC best practices. A lot of the things that we've done historically apply very well to deep learning and to the frameworks and the core algorithms. A lot of our focus has been on reducing the total workflow time, around training. We know that the largest models are now hundreds of layers. The one that we show here in this small picture is not a particularly complex neural network. In millions and billions of nodes, the data that we're talking about for training, it just seems to keep growing and growing. So. After everything's processed and we've tuned and we've optimized hyperparameters, that's once we've dialed that in, then I think we'll have a better handle on time cycles for deep learning training cycles on particular data sets, and we're able to better forecast based on what we think the growth rate of that data set is. Okay. So there was a paper by the folks at Google called Large Scale Deep Learning for Intelligent Computer Systems. The key takeaway here is that if you're starting off with a model training exercise that's takes greater than a month, don't even try. If it's 1 to 4 weeks, you're in the experimentation phase. That may or may not be okay. You're going to see progress stall out probably periodically. 1 to 4 days is tolerable. A lot of the interactivity is ultimately going to be replaced by running many experiments in parallel, and I think we've seen this in the HPC world, from our end users. Really, the true nirvana state is minutes and hours, where interactive research and instant gratification. That's ultimately what what I think our user base is looking for. Okay, so I threw this in. We did a kind of an experiment with Microsoft and the folks at the Swiss Supercomputing Center in November, December timeframe of last year, where we took Microsoft's cognitive toolkit and we actually scaled it up. So we have kind of some of the performance there shown at starting at 64 nodes, and we actually scaled it up to 2,048 nodes. So these are number of GPUs. So this is on the PISDATE system at the Swiss Supercomputing Center. And this was really an interesting exercise. It wasn't we had to do a lot of work with Microsoft on updates to the code base to be able to get that code to scale, get this type of linear scaling on that code. It is possible. And it's a lot of it's going to depend on what's your qualification for response time on training data sets. Okay, running out of time here, so we'll kind of quickly run through here. Another reference, again, paper by some smart folks at Google, adapted from this is Hidden Technical Debt in Machine Learning Systems. Only a fraction of real-world machine learning systems is composed of the ML code. So that's the black box in the middle here, and you see the supporting ecosystem that sits around it. So there are lots of other pieces to this. Some of the data collection, the streaming components, how we classify and categorize data as it's coming off the wire. These things are all incredibly important, and to some degrees, they're going to dictate whether or not you're successful with your implementation. So again, we've kind of driven this point home, but the artificial intelligence is a workflow, and we think HPC can really support a number of steps in that process. We're starting to see big data analytics applications running on HPC systems, as well as deep learning toolkits. We do see through containerization the ability to kind of leverage similar types of systems to perform different functions, and kind of quickly and easily reconfigure and reprovision those systems for those workloads. Finally, we'll wrap up. AI is everywhere, even the grocery store, right? So Amazon completed their acquisition of Whole Foods. Whole Foods had it as their farm fresh pick of the season. You could get an Amazon Echo in the grocery store. So we know worlds are converging at that point. So. All right, that's all I've got. Questions?
Any questions?
I'm glad I didn't get the question on Putin or Elon Musk. So that was that was
here
good.
It comes. No. So how do you, as Cray, decide what part of the AI market to carve out to target? I mean, what attributes are you looking for as you kind of look at specific parts of that market? Because obviously the mainstream might not need HPC yet.
Yeah, absolutely. No, that's a great question. And I think you'll notice throughout our presentation, a lot of the focus was on deep learning training. We really think that's where the opportunity is for us as Cray. A lot of the other steps in the process, those could be, more performed on commodity clusters. We certainly have offerings to do the analytics pieces of the workloads as well. One of the interesting things that we're seeing, though, is from some of our HPC centers that are customers of ours, we're seeing a lot of their users kind of demanding access to some of the deep learning toolkits and capabilities, as well as analytics capabilities. And a lot of, this is the convergence story that we've been talking about for a while. And some of the technologies that we're kind of investing heavily in now are, software to get more mileage out of your existing investment.
Any other questions?
Yeah, sure.
You've mentioned amazing scaling of deep learning workload on Cray system.
Yes.
To the thousands of nodes. Was it weak scaling on strong scaling? And if it was weak scaling, did you measure convergence of the model?
So
what
that's
about accuracy?
Yes. So good question. And so as a result of that exercise, I often say we have one of the best benchmarking teams at Cray. But one of the things that we've been having to get them kind of ramped up on is how you benchmark deep learning applications. And so speed is one component of that, but time to accuracy is another big component. That particular exercise, we weren't as successful with time to accuracy as we would have hoped. So our next kind of iteration of this is to kind of, we've got our benchmarking and performance guys really working on optimizing, MPI for that type of scenario, so that we can, make sure first that we're performant, but that we're also
accurate as well too. But it's a great question. It's not always about speed, necessarily. The accuracy is a huge component.
Okay, Tim, thank you very much.
Thank you.